One thing, I guess something that's fairly vital when you're talking about a class about exoplanets is got to first identify what an exoplanet is, which one would think that this was or this had been done, but there are kind of wrinkles to this. So let's start with the basic. What is the official astronomical definition of a planet? This came about, I'm not going to get into the gory details, but this came about because of Pluto. So there was some contention within the astronomical community as to whether or not Pluto should be considered a planet or be considered basically just a small solar system object like a comet or an asteroid or what have you. Uh, you will probably not be surprised to know that the primary motivator of this discussion wasn't really physics, but money. But that's a side point. Anyway, in 2006, the International Astronomical Union, or IAU, convened its annual meeting. And in this meeting, they put forward three different definitions of what a three definitions of a planet to be voted upon by the members present. The one that won out is this one. And a I am on the record as saying that this definition is stupid. But let's look at the definition, and I will go over why I think it's stupid. So the definition reads simply as a planet is a celestial body that is in orbit around the sun, has sufficient mass to assume hydrostatic equilibrium. That means roughly speaking, it's a sphere. And three, it has cleared its orbit. What does that mean? Well, that means that it is a bully, effectively. It is it has gravitationally cleared away any other object within its orbital path of comparable mass. Basically, there is no other there is no other Earth in our orbit, for example. The only thing that might cross our orbit or be near our orbit are things that are much less massive than the Earth. When the solar system was very young, there was a lot of planetesimals, there was a lot of asteroids, comets flying around, and over a fairly short period of time, uh, the gravitational influence of the planets basically swept them away, or the bodies slammed into the surfaces of said planets. So, why does Professor Parks think this definition is stupid? Well, because let's take the first point in orbit around the sun. So, from a technical standpoint, there are only 8 planets in the universe that we know of at this point. There might be a ninth, but that's still possibly in possibly in flux. So, all of the objects that I am going to talk about in this course, according to the IIU, are not planets because they do not orbit around the sun, which I think is a gross admission, omission uh, for the in this case. And this is 2006. We had known about exoplanets for at least 10 years at this point. So it's not like they didn't know that exoplanets existed. They just, for whatever reason, ignored that they did. The second point is the only one that I like, which is the body is of a sufficient mass that it is spherical. The reason why I like that is because it is a physical characteristic of the object. It is not location dependent. And something else that I forgot to put in the slide deck, but I'll talk about later, is that there are planets that have been discovered that do not orbit anything. They are, in fact, rogue planets, or they're called rogue planets. They are freely floating throughout the galaxy. They once Presumably, we believe that they formed around a star, but because of gravitational interactions with other things, they got ejected. Basically, they got punted out of the solar that stellar system. So again, the first point is location dependent. The second one is actually physically motivated. The third, you might think is physically motivated, and to a certain extent it is, but it is also location dependent. The reason for that is if you had taken Pluto and put it in Mercury's position, it would have cleared its orbit. But the fact of the matter is, Pluto moves so slowly and has such a large orbit, it hasn't had time to clear its orbit. And so there's a temporal component there that I also don't like. So, so that is the official definition of a planet. What is Dr. Parks's definition of a planet? Well, that's easy. Definition of a planet is an object that has enough mass, that is spherical under its own weight, that formed around a star. That's it. Now, if you were to apply that definition to the solar system, yes, that would mean that we have not 9 planets, but I think we're at 12 plus at this point. So, and potentially there are many, dozens more to be discovered out there. That doesn't bother me, but apparently some of my colleagues, it bothers them. But enough of that, enough of my pontificating. Make Pluto great again. Let's move on and talk about the history of exoplanet science. Um, I like bringing this up because not only is it sets the stage for how we got here in terms of finding exoplanets, but it also is a very good case study for how the scientific method is employed. So, with the scientific method, very briefly and very crudely, basically you observe something. You observe a physical phenomenon that is in reality. Oops. And then you make a guess as to why that phenomenon has occurred or whether or not that phenomenon occurs other places. So in this context, the observation is we see planets going around the sun. We also see stars in the night sky, and we believe that those stars are the same as the sun. So the hypothesis would be, are there other planets going around those stars like they are going around the sun? So you have a hypothesis. You then develop an experiment or some kind of technique to answer that question. You then implement that method and see if you're correct. And what's important is, and what's often glossed over, is that in the scientific method, one of the more important aspects of it is that this is not a one and done, is that you do the experiment, you get the results, and then other people also do the experiment and ultimately see if they can verify your results or not. And as technology progresses, it's possible that something that was missed by an earlier astronomer can be detected because now you have better instruments to do so. You continue that process, and after every experiment, you then, and this is probably the most important thing, is you tell people about it. You write a paper, you publish it, because as a colleague of mine likes to say, science unpublished is science not done. Science not published is science not done. So you got to tell people about it. So let's start off with the hypotheses. Now, speculations of exoplanets have dated there have been people who have thought that exoplanets existed for hundreds of years. Now, even before the time of Copernicus, there were these group of scholars known as Neoplatonists, and they speculated as to the existence of a plurality of worlds, as they say, in the fact that the solar system is not the only system of planets out there. Granted, in the early days, the Earth was still the center of things. The Earth was still the center of the universe, but it was thought that maybe on those stars there were also other planets. The most famous hypothesis was put forward by Giordano Bruno. In one of his writings, he states, "This space we declare to be infinite. In it are an infinity of worlds of the same kind as our own." Now, he was a priest or a monk. I can't remember exactly what his designation was. It doesn't matter because he left the church. Um, so he was a religious man. He believed in God. He believed in the creation, and but his his philosophical thought was God's creation was infinite. So if it were infinite, then you would see the same types of behavior everywhere in creation. So if you saw planets around the sun, then you would see planets around other stars. Bruno is often held up as this martyr to science because ultimately he was burned at the stake during the Inquisition. And it is often said that he was burned because of this hypothesis that he came up with. That is not accurate. Did he say it? Was it one of the articles that he was charged with? Yes, but there were theological reasons which caused his death. So I only say this because it irritates me when people think that Bruno was a martyr to science. He was not. If you look into his life, he was about as anti-scientific as you could possibly get. But he was one of the first to write down and to advocate for the existence of exoplanets. Isaac Newton joined in. Basically, he had the same reasoning. In 1713, he wrote, "And if the fixed stars are the center of similar systems, they will all be constructed according to a similar design and subject to the dominion of one, or God." Meaning that those systems will obey the same physical laws as we see here. They will obey his laws of motion, they will obey his law of gravitation. So let's move to from hypotheses to experiment. Now that we have this idea, now that there are a number of people who have postulated the existence of exoplanets, how might we find them? Oh, um, so yes, I just so folks know, I am recording this lecture, and so I will be posting this later on once Zoom is done downloading it. Hello, Luna. Yes, yes, cat. Okay, don't fuzz in my coffee. All right. Anyway, um, Luna. Sorry, my one of my cats. Anyway, so getting to the formula, so getting to testing this hypothesis. Well, one of the um, more famous or one of the more useful techniques that has been developed was actually first developed in 1952 by a gentleman by the name of Otto Struve. He proposed using an effect of light called the Doppler effect. Now, we have more than likely you have heard of the Doppler effect in terms of sound, but effectively what this means is that when a wave, be a sound wave or a light wave, when that wave is being transmitted to you and the space between you and the transmitter is getting shorter, then the frequency of that wave goes up. So in terms of sound, that means that you have a higher pitch. In terms of light, that means that the color of the light becomes bluer than it would be if it were sitting still relative to you. And then the opposite is true. If something is moving away from you, then the pitch or then the frequency goes down, the pitch drops, or the object becomes redder. And so what Struve suggested was if you have a planet, a mass going around a star, so like so, Then, and you look at the light of the star, then you might notice that the star will periodically become bluer, redder, bluer, and back again. The reason for this is because gravity, it works both ways. Gravity, when say take for instance the sun and Jupiter. The sun exerts a gravitational force on Jupiter, which holds Jupiter in its orbit. But Jupiter also exerts the same amount of force on the sun. And so the reason why Jupiter appears to orbit around the sun is simply mass. Jupiter has a much smaller mass than the sun does. And so the sun appears to stay relatively stationary in respect to Jupiter. Excuse me. But if you actually measured carefully, what you would notice is that the sun's position relative to some arbitrary outer framework actually moves fairly chaotically. Because of the interactions, because of all the planets, the sun wobbles in its place within the solar system. And so Struve realized this and said, "Hey, this sort of thing should happen to other planetary systems. They should exert some kind of force on their host star, causing that host star to move relative to us closer and further away. And if you could detect this, then you could potentially attribute this to an exoplanet." But this was 1952. Spectroscopy at the time was still fairly crude. It was only about, as a field of study or as a technique, it was only about uh, 70 years old or so. And so it was very crude. So the amount of shift that one would predict for Jupiter going around the sun, the amount of shift you would see into the blue or into the red is minute. It is very, very small. So you need very high precision, very sensitive instruments in order to detect it. Unfortunately, 1952, they were nowhere even close to having this kind of technology. So the technique, while sound theoretically, basically sat on the shelf for a while. Now, as I said, you still there are other people developed other types of techniques to try to find exoplanets, also based on the idea that the planet has a mass, and so it's going to exert a force on the star, and it's going to cause it to move in some way that it would not do if it were by itself sitting in space. And so there have been false claims. There have been a couple of different claims that have been made that have been then found to be false. And what I mean by that is other people use the same technique or looked at the same data set and were not able to determine or were not able to arrive at the same conclusion that the original scientist found. One of the notable experiences of this was the binary star system 70 Ophiuchi. Very sexy name, I know. Effectively, you have two stars that are orbiting around a common center of mass. Now, if you just have two stars that are orbiting around each other, they basically have very similar, if not exactly the same mass, the point of rotation is going to be in the middle, and they go around each other. This is a very stable, these binary systems can be very, very stable, meaning that the period does not change appreciably over thousands, if not tens of thousands of years. They're almost like clocks. And so when they looked at the signature, the light signature of this binary, what they noticed was that the period of the binary, the time it takes for the stars to revolve around each other, was not constant, that there was an irregularity in the period. And so they hypothesized that there had to be a third mass in that system effectively throwing things off, adding another piece of gravity into the mix and causing things to be a little bit more chaotic. Unfortunately for them, a mathematician by the name of Moulton was able to demonstrate that no matter what size mass you put into it, that system would not be stable over any length of time. When I wrote down that it's a dark planetary body, it's notable. It should be noted that the in this case they don't see the evidence of light, and that's important because that limits the mass of that object. If it's of a certain mass, it's going to glow either because of thermal energy or because of the fact that it's burning nuclear fuel. So Moulton, because of that, Moulton was able to basically put in a range of masses for a third body and see and mathematically predict what that system would do over time. And what he found was any third body would throw that system into chaos. Basically, the stars would either collide with themselves or the system would come apart. Now, is it possible that there is a third body there and we're just happening to see it in just the right time where the planetary system or the stellar system is stable? Yes, possible. Is it likely? No. It is not likely that we just have by happenstance to see this very unstable configuration at just the right moment. And so effectively, it was the community said, nope, nice try, but you have not found the first planet. As it happened, Jacob was like, well, that sucks. And then, went on with it, with his life. C, on the other hand, would not accept this. And unfortunately for him, as opposed to the guy that I'm about to talk about, he was not very well established within the community. And effectively, he wrecked his own career by doing this. He refused to accept that Moulton's analysis was correct. He refused to accept the evidence that was contrary to what he had to say, what he believed. And as a scientist, that's not how things should be done. As a scientist, one should be open-minded to the possibility of being wrong if the evidence to suggest that is strong enough, which in this case it was. Now let's go to the case of Peter Van de Kamp. Van de Kamp made his bones in a field known as astrometry. Van de Kamp was one of the pioneers, or one of the people who was able to determine the exact positions of stars at any particular time. He was very well established. He was a very well respected astronomer. So when he made the claim that Barnard's star showed irregularities in its motion, which seemed to indicate the existence of an exoplanet, people perked up. And so a lot of people turned their own telescopes to Barnard's star to see if they could replicate the data that is shown on this slide. What you're seeing on the slide is the position of the star in right ascension, which is basically stellar longitude, and declination, which is basically stellar latitude. And you can see that the star's position in longitude changes as a function of time, and also in declination, in latitude as a change of time. Now, Newton would tell us that an object in motion is going to stay in motion in a straight line unless acted upon by an outside force. So if Barnard's star was just a single star, it would move in a straight line. Its RA and dec would not change as a function of time, because that's basically fixed on the celestial sphere. But he sees that it varies. And so the implication is there has to be something causing that. There has to be a force causing the star to effectively wobble in space. And that force would be gravitational in origin because he can't see it, because he doesn't see the light from it, and because the variation is very small. It's the conclusion he came to was that it was in fact a planet that he was seeing. Unfortunately, no one could replicate his results. He studied this star from Lowell Observatory. Anyone else who used another telescope and attempted to get the same results that he didn't find it. They basically all found that Barnard's star was fixed in space, essentially, that its RA index did not change appreciably over time. Now, I have not heard I have not heard a lot of supporting evidence to this, but the consensus is effectively there was some kind of systematic error in Van de Kamp's setup. Effectively, there was some kind of vibration in the telescope or optical system that he was not aware of and was not accounting for. That's the line that, or that's the consensus uh, that there was at the time. Van de Kamp did not accept this, and he went to his grave believing that he did in fact find the first exoplanet. As it turns out, there is an exoplanet going around Barnard's star. As I said in the first lecture, there are planets everywhere. If you have a star, you probably have a planet. And so eventually one was found, but it would not have caused the signature that we see that Van de Kamp saw. So he was right, kind of. I don't know if that would be of any comfort to him. Now, the first exoplanet happened to be the in my opinion the weirdest. And again, mentioned this in the first lecture, is that the first exoplanet wasn't found around a typical star like our sun. It was found around a stellar corpse, a star that
Ah,
had gone supernova and was going out the rest of its life as a pulsar. Pulsar is a very small, compact ball of neutrons that is producing or emitting a beam of radiation, very much like or off its poles. So one beam is going in this direction, and there's an opposite beam going in the other direction. That beam is not always aligned with the rotation axis. So when this neutron or when this spins, when this ball of neutrons spins, that beam of radiation can sweep out through space. If we detect this, then we call it a pulsar. I mentioned before that binary systems were like a clock. Pulsars are even more so. They are cosmic timekeepers. The period is stable to a ridiculous precision. So when Walzy, I can't remember his name. It's something Polish that starts with a W. In 1992, he discovered around the elegantly named PSR B1257 plus 12. He noticed that the change in the period of the pulsar was periodic. What that means is that the period was in some cases slowed down and in other cases sped up over time. And again, the best explanation for why that would be the case is if something was tugging on it. And so, because there was a mass, it was affecting the timing. The timing difference is minuscule, but because pulsars are so regular, this was not something that could be ignored. And it turned out that the detection was actually of an Earth-sized planet. Um, there have actually been comets to be discovered around this, or objects that are the mass of typical comets going around it, to tell you just how precise this particular method is. Now, do we know where these planets came from? No, or at least I haven't heard if whether or not they have determined whether or not these planets survived the cataclysmic supernova, or if they were actually formed in the cloud of the in the supernova remnant. As far as I know, uh, There may have been a couple more of these discovered. We'll actually find out because in a slide, I'm gonna tell you how many exoplanets have been discovered by methods. Then in 89, well, actually, a few years earlier to that, a team from Harvard looked at gamma Cephei AB, a team led by David Latham. This is by some people, they call this Latham's Planet. In 1989, they actually used Struve's method. They used the Doppler effect to see whether or not they could see if the star is wobbling. And if so, if it is wobbling, if the Doppler signature matches that of a planet. And they detected something. The signal that they got seemed to indicate that an exoplanet was there. However, it was pushing the limits of the technology, meaning that the signature wasn't very much bigger than the error of the measurements. And so, while it was possible, the community did not accept it as an exoplanet because it had not been definitively ruled out that this was a detection and that this detection didn't correspond to some other astrophysical phenomenon like star spots or stellar pulsations or something like that, which we have seen in other systems with other stars. Eventually, in 2002, it was confirmed. Enough observations were taken, the technology advanced sufficiently enough that when we looked at gamma Cephei AB with enough, basically with enough precision sensitivity, that yes, Latham was correct. There was a planet. But again, this is an aspect of scientific discovery, is that when we talk about exoplanets, there is a difference between discovery and confirmation. So there are a number of, I think I checked, well, actually, it's in the next slide. We'll see the numbers. But when you look at the number, if someone were to ask me how many exoplanets there were that we know of, well, there are roughly 6,000 of them that we have confirmed, meaning that they have been so well studied by enough researchers using different techniques that it is almost impossible to come up with an astrophysical situation to explain the observations that we're seeing. They don't match star spots. They don't match stellar pulsations. And then you have planets that have been detected but not confirmed. So essentially, Gamma Cephei was detected in 1989, but confirmed in 2002. So any detected planet is really more appropriately called either a object of interest or a candidate planet. Eventually, but finally, the first confirmed planet around a star similar to our sun is the famous 51 Pegasi b. Again, it was used by using the Struve method, and it found a planet that, or a massive body that was about half the mass of Jupiter, that is orbiting around its star 10 times closer than Jupiter. To put it another way, a year on this planet is around 4 days. That's how close it is to the star, and that's how fast it's moving. And it caused a huge stir because, one, it was the first, it was fairly easily to confirm because the signature was large in comparison to the technology at the time. And so it was very quickly ruled out that this was anything but a planet. But then it caused a stir because of the mass. The mass was half that of Jupiter. And by how we know planets to form, it had to be gaseous. And particularly when we found out what its size was, what its radius is, what its density was, this thing had to be made of a substantial amount of hydrogen and helium gas, which means like Jupiter, which is was completely unexpected because one, according to our theory at the time, Jupiter's cannot form that close. And two, it's so close to its host star that the temperature is around 1500 Kelvin. One would have expected the star to, or the planet to literally evaporate, being that hot. But again, more studies were made. More people through came up with theoretical models, and they determined that yes, a Jupiter planet can form somewhere else in the solar system and then move closer to the star, stop in a circular orbit, and survive for at least a billion years. So that was that really was an exciting moment. All right, let's talk about the current state of affairs. We have that there are, as of the 15th of January this year, we have confirmed the existence of 6,080 planets. So we are, you know, set that these are in fact planets, meaning that it would take a significant amount of evidence to convince the community that these are in fact not planets, that these are some other phenomenon. Because TESS, which is the transiting exoplanet satellite, that's what TESS stands for, or satellite survey, transiting exoplanet satellite survey. Because TESS is really the only the only thing that is dedicated to finding planets. The archive basically highlights it. So at the moment, 733 of these planets have been detected by TESS and have then been confirmed. But the more important number in this discussion is the next one, which is that there are now 7,821 TESS objects of interest, or TOIs. These are detected signatures that could very well be explained by a planet, but need follow-up observations. As it happens, we have done that here at George Mason. Our telescope has been used to look at these candidate planets from TESS, and we have confirmed about 50 of them. So of that 733, 50 of them were confirmed using our observations from our telescope. And I'm hoping to be able to restart that program sometime fairly soon. Because when it comes to confirmation, you need a lot of observations. You need a lot of dedicated telescope time. And for a lot of these for a lot of these objects, they're fairly dim, so you need a fairly large telescope. And unfortunately, if your telescope is of a significant size, then a lot of people are going to want to use it. And so you don't have a lot of time to dedicate to one particular object. That is why our telescope kind of fits into the sweet spot of it's large enough to get the job done, but it's not so large as to be highly demanded by other scientists. So, methods. There are a range of methods at this point. You have astrometry, which is the change in the apparent position of the star over time. There is direct imaging, actually taking an image of a star, of a planet going around a star. There is a radial velocity, that is the Doppler effect or the Struve method. There's transit. Basically, the planet travels in front of the star, blocking out some of its light. There are transit timing variations, meaning that while you can't exactly see the second planet, its gravity is affecting the orbital motion of the first planet, the one that you can see. And very much like how I was talking about with the pulsar, it's going to cause the time of transits to alter, to vary because of that, of its presence. And so we found a small number of them that way. Eclipse timing, that would be the Ophiuchus scenario where you have two stars going around each other, and then the timing would be affected by a third body. In this case, the addition of a planet is not going to cause the system to break apart or collapse in any way. Then you got pulsar timing. So I guess, yeah, we have now 8 pulsars that have planets around them. Pulsation timing, um, orbital brightness modulations, and disk kinematics. Orbital brightness modulations, I think, is another way of saying, um, oh no, I forgot about microlensing. Microlensing is cool in that these all of those planets, the microlensing, this 263 planets detected by microlensing are all rogue. These were found, or no, scratch that. I'm completely wrong on that. These were found by a star going in front with a planet going in front of another star that is way in the background. And because of general relativity tells us that light bends in the presence of mass. It actually can lens, it can focus the light of a background object and cause it to change its appearance or basically change its location, or in this case, brighten significantly. And if you have kind of a double peak to it, then there are two masses that are very close to each other. And again, you can model what kind of signature you would expect for a Jupiter-sized planet to be moving around a sun-like star with an orbital period of, or a distance of 1 AU or what have you. And so they have been found. Incidentally, microlensing has been also used to find rogue planets. The problem with I'm going to go into a number of these methods in specific later on. I'm going to be spending most of my time on the transit and radial velocity methods because, as you can see, they account for the the largest majority of exoplanets that have been discovered. They are the um, not easiest to do, but they're the most reliable sort of workhorse ways of doing it. So I'm going to go into those in fairly good detail. But I will talk about microlensing a little bit more. Each of these methods, all the methods that you see on the screen, have their pros and their cons. They have what is known as a selection bias, meaning that these methods are very good at detecting certain types of planetary systems. And so this needs to be recognized because you might think that, for example, in the early days of exoplanet discovery, we were finding a whole lot of hot Jupiters because massive planets very close in are easier to detect using the radial velocity method than planets that are further away or smaller. So if you looked at the face of it, you might say, oh, hot Jupiters are very common. It seems like most planets are hot Jupiters. Well, as it turns out, again, with more study, with better technology, hot Jupiters make up a fairly small population of the planets. So when we look at these things, we have to acknowledge that there are certain limitations to these methods that might lead us to false conclusions. Microlensing has the problem in that it's a one and done. With radial velocity in transit, those are still going on. So you can actually, if we were using our telescope, I could go to an exoplanet that has been confirmed. I can determine when the next transit is. I can look at that star using the telescope and I can see that transit. The evidence of the planet is still observable to this day. Microlensing is a chance encounter. Basically, you have the planet moving in front of a star that is far in the background. Now, while there are a lot of stars out there, there are not a lot of stars out there of sufficient brightness that you would be able to see this sort of microlensing event happen multiple times as the planet moved through space. Or at least we haven't figured it out yet. So when it comes to the microlensing planets, I'm a little bit uh, um, cautious because of the fact that we cannot verify these with subsequent observations. All right. Let's roughly just talk, show you some numbers. How many planets we've discovered by mass and radius. Uh, Again, going through the different techniques, certain techniques can either give you the mass of the planet or the radius of the planet. Um, and if you can combine those methods, then you can actually determine, well, both. Um, when we look at the masses, might notice down here the last column is 300 Earth. This is Earth mass. So the 300 times the mass of the Earth. This is the lowest. This is basically a Jupiter. So it's saying that of the population of confirmed planets, 763 of them are of Jupiter mass or greater. And you can see that it's a fairly even distribution of planetary mass from what we call super Earths, so terrestrial bodies that are just two, three times as massive as Earth, through Neptunes, and then back into Jupiters, or planets that are about the size of Neptune, Uranus, and then into Jupiter. For the most part, that distribution is approximately even, which has implications as to how these systems formed. When it comes to radii, this is probably due to a selection effect in terms of how we find these. These are m mostly discovered through the transit method. There seems to be a spike in the data between 2 to 6 Earth radii. We find a lot more of them that are that size than we do that are smaller or larger. Again, this might be a selection effect. Um, oh, I didn't actually add it to this presentation. Now, I talked about in the first lecture, I talked about that um, there are lava worlds, there are water worlds. The way that we know this, or rather the way that we suspect that these cases of these planets are composed of a great deal of lava or a great deal of water is simply its density. So the Earth's density is around 5.5 grams per cubic centimeter. That corresponds to a basically a large ball that is composed primarily of magnesium silicate and oxygen, or magnesium silicate, uh, which is MgSiO3. Yes, it does have elements that are denser, like iron, nickel. It also has elements that are lighter, like aluminum. But in general, that is a signature. If we have a density of a world that is similar to that, then it's similar to the Earth, and so that is how we have determined that the planets going around TRAPPIST-1 are most likely terrestrial because they all have densities that are very similar to that of the Earth. If you have a density that is, um, you can also look at it in terms of temperature. So if you have one of these terrestrial planets that is really, really close to this host star, it can actually melt, or if it's really young. So there are other factors involved in determining what kind of world it is. But that's how we go. Actually, you know what? I am going to. Uh, I'm going to go to the source of all knowledge, not ChatGPT. I'm old school. Um, let's see here. Oh, no. Let me see if I can find it. Wikipedia has a very nice graphic that I want to show. Um, and I want to see if I can find it. I know I downloaded it. There it is. So there are a lot of different ways that you can look at the statistics of planets. In the plot that I just showed you, you can look at it as a function of um, mass and radius. So effectively, density. You're looking at the planets as arrayed in a density formation. Or you can look at it in term like this, where share. Or you can look at it with like this kind of graphic, where you have size of the planet relative to Earth as a function of orbital period. And you can see that there are different, we have designated certain regions as where certain types of planets are going to be found. So hot Jupiters, generally speaking, have sizes that are of this of 20 to 10 to 30 times the mass of Jupiter or mass of the Earth, and their orbital periods are generally speaking less than 2 weeks. Cold gas giants like Jupiter itself um, are have orbital periods of thousands of days, and again, they also have sizes that are roughly the same. This is also a good time to talk about observational bias or selection effects. Down here, when it comes to frontier, we have not found any planets. We have, and actually, you can kind of see that the line is, kind of you can draw a diagonal line upward, and we have not found any planets that are in the bottom right. Does that mean there are no planets to be found that are small in mass but long in period, meaning that they orbit around at a large distance around their host stars? No, that does not mean that that is the case. What that those planets are difficult to detect because one, the small mass and the large distance means that the gravitational effect on the star is difficult to detect. That it is much less than if that planet were much closer to the star, because gravity is an inverse square relationship. The closer it is, the bigger the gravity, and the easier it is to detect. The other issue, which is becoming just simply, we just simply have to wait, is that, you know, stars take or planets take a while to get around in their orbits. If you look at Kepler's law, the fairly straightforward version of it is that the period of the orbit squared is equal to its semi-major axis or size cubed. So you can put in the numbers and you can figure out that, it takes for Uranus and Neptune, it takes hundreds of years for those planets to go around the sun. So we're not able to confirm the existence of those planets until we have data that spans centuries. So when it comes to trying to find a system very much like the solar system, the main problem is time. We just have not been looking long enough to be able to find Jupiters and Saturns that are analogous to our own, meaning that these are planets of similar masses that are located in similar positions. So this is an example of a selection effect of we just haven't looked at things long enough, and the planets that we have looked at are not overly massive. That is not to say that maybe there are legitimate gaps where planets cannot be formed or cannot be found. Like for instance, over here, you see that when between say 4 to 10 Earth masses, there doesn't seem to be a lot of planets discovered, but there are a lot of planets discovered above, and there are a lot of planets that are discovered below. A lot more massive planets at the same distance, a lot more less massive planets at the same distance. What this tells us as astronomers is that this space, or these characteristics of mass and orbit, or massive orbit size, has been very well studied. And so this gap is not a selection effect. This gap is real. There is some physical reason for why planets do not generally have masses between 4 to 10 Earth masses and orbital periods that range from 1 to 5 days. There is something that prevents planets from hanging out in that, either being created or hanging out with those characteristics for any length of time. So a lot of exoplanet science is basically looking at plots like this and trying to figure out correlations of, do these planets have similar characteristics? Is there a trend of, do planets become more massive as they move further out, or do they become less massive? So it's a whole lot of statistics when it comes to statistical analysis, when it comes to looking at exoplanets, which I know may sound boring, but well, yeah, it kind of is boring. But to each their own. There are people out there who really love that sort of thing. Oh, hold on. Bring this PowerPoint. Nope, that's not what I wanted either. Oh, maybe it is. Nope, this is not what I wanted. What is going on here? Go away. Current slide. It's as if I've never used Zoom before. Okay. So I'm going to finish off today by talking about types of exoplanets. So let's start off with the easy ones, or the most familiar. Terrestrial planets. Terrestrial planets are planets that are made of rock, and they're fairly cold. So this rock is solid in its configuration. Again, they generally speaking, with terrestrial planets, you have an iron core, a silicate mantle, and then a crust of lighter materials. If you look at the structures of of Mercury, of Mars, Venus, Earth, generally speaking, the first order, they're identical. They all have a iron core, a lighter mantle, and an even lighter crust surrounding them. And so we believe we have found analogs of these. We've found other terrestrial planets around other star systems. So we can confidently say now that forming terrestrial planets, yeah, that happens pretty much all the time. Then you have a type of planet called an ice giant. An ice giant is a planet that is roughly the size of Uranus and Neptune in terms of mass. So we're talking about a mass that is a couple, around 10 times the mass the of the Earth, and again about 10 times the size, tens of times the size and radius of the Earth. And so Neptune's and Uranus's. So we have two in our solar system. We have found these around other solar systems as well, or other stars as well. So again, forming ice giants, not unusual. Then, of course, you have gas giants. Now, in this case, I'm showing you a sampling of the different gas giants that have been detected. HAP P12b, WASP 17b, and so forth and so on. These are planets with densities that would indicate that these are just normal gas giants like Saturn, Uranus, or Saturn and Jupiter. Again, we're basing this on the density of these worlds. Jupiter and Saturn have densities that are pretty close to one, or pretty close to 1 gram per cubic centimeter, or thereabout of water. So you have a density that is around one, but you have a size that is, you have a mass that is hundreds of times the mass of the Earth. And so the only configuration of matter that can replicate that is a culmination, or is just a collection of hydrogen helium gas. Then we have found that there are planets in existence that do not have Earth analogs, such as ocean worlds. Examples of those are GJ 1214b, Kepler 12b, 22b. These are planets that are more massive, larger than the Earth, but their densities are higher than ice giants. their densities are about the size, or their densities are about that of water, meaning that we believe that these planets probably have some kind of rocky core, but then they're covered in almost a mantle, or and definitely over its entire extent, of ocean water, of water of one form or another. And so examples of these are GJ 1214b, Kepler 22b, so forth and so on. Those names, those indicate um, Kepler, for example. That is, this planet was found by the Kepler satellite, and it is the 22nd object that was studied by Kepler. Um, GJ 1214, that actually is the designation for the star. So that star had been known before, and so that doesn't actually indicate the discovery instrument. It just indicates the well-known studied star around it. And then we have lava worlds. We have worlds that again probably are basically terrestrial, but because of their location and their age, they are covered in lava. They're effectively just massive volcanic worlds. The best analogy, or the best analog we have, if you were to look for it in our solar system, is the moon Io. Io, there are dozens of volcanoes going off every single day, if not more. Almost every hour, you're going to have a volcanic eruption somewhere on the surface of Io. The surface is literally a hellscape. It's sulfur and brimstone. It would smell really, really bad, assuming the atmosphere was actually dense enough to experience it. And so we believe we found these worlds, basically just giant versions of Io, Crow 7b, Kepler 10b, so forth and so on. And then finally, this is pushing the envelope when it comes to exoplanet science. This is kind of the next frontier. This is where JWST is expected to play a large role. Is all right, we have found that if you form a star, you form planets. Well, if you look at the gas giants and the ice giants, all of them have moons, and all of them have a large number of moons. So, if you form a star and you form planets, is it therefore also like, or also the same as saying if you form a gas giant or an ice giant, you also form moons? And so we're trying to find signatures of those moons. In terms of SETI, in terms of the search for life, this is also very important because we believe that the moons of Enceladus, of Titan, of Europa, these moons of other worlds may also be suitable for the existence of life. And so the study or the search for these exomoons plays into that. If we want to understand how life came into existence, the environments from which life could exist, possibly find aliens, then we also need to have a complete description of these systems, and we need to figure out whether or not these moons actually exist. It also has implications into the mechanism of how things form. If we find out that we cannot discover exomoons, that the moons around Jupiter and Saturn are a one-off, then that tells us something very significant about how our system formed, that our solar system is weird in some way. But chances are we are going to find that there are exoplanets out there with moons.